Okay, hello. Hi. Well, my presentation today is going to have a Doctor Strange theme to it. So if you haven't seen the movie, the multiverse of madness, some of this, hopefully can still make sense. But the idea that I'm trying to convey here is that sometimes things are difficult to do in one universe, but become amazingly easy to do in another universe. So what I'm proposing here is we change the way we think of how we build a website, and perhaps things that are hard now can become easier in the alternate universe. But yeah, a bit about me. I am a lead sorcerer at DiUS Computing. DiUS is a company based in Melbourne, but we also have an office in Sydney. I know marketing is online right now, so I need to say a few words about this. So we're about 150 strong, 18-year-old company. I've been there 12 years myself, so I've been there a long time. And we specialize in using emerging tech to design, develop, and deliver cutting-edge solutions. We actually have people spread all throughout APAC now. We've got people in Japan, New Zealand, and various other states throughout Australia as well, due to COVID requirements. Hope that's enough, Aaron. Okay, all right, so a bit of background. At the start of this year, I was asked to see if I can help improve an e-commerce website. I won't give names to protect the innocent, but I wasn't satisfied with the usual, like, code splitting, lazy loading, finding a lighter equivalent of packages and whatnot. I wasn't satisfied with that because I felt like doing all of that can only buy me fractional gains, like improve it 5%, improve it 10% if I'm lucky, right? That wasn't good enough for me. I wanted to go further. So I started thinking about how we build websites in general and realized that we can actually go much, much further. So my main aim here is primarily performance from the user point of view. But if you stick with me for a while, you will see that the performance here will also refer to developer performance as well as we build sites even faster. Okay, why does performance matter? Because every millisecond counts, right? Over a decade ago, Amazon said 100 milliseconds equals 1% of sales. And then Google said extra half a second, drop traffic 20%. Akamai said, what do you mean 100 milliseconds equals 1%? 100 milliseconds to us means 7%. So quite big. Google also said that the bounce rate increases. As you start from 1 second and you increase that to 3 seconds, your bounce rate goes up 32%. It goes up to 5 seconds, it's up by 90%, and so on and so forth. So performance really, really does matter. Now, of course, this is dependent on your actual site itself, right? How much traffic you're actually getting, how elastic your traffic is, and where your baseline actually is. 100 millisecond change at 2 seconds is a very different story to 100 millisecond change at 5 seconds, for example, right? So, your mileage may vary. But even if you're not selling anything, if you're not an e-commerce site, if you're a site that does other things, making a fast site is just something good to do. Think of your users, right? Okay, what's going on here? Cool. And developer performance as well. Often we tend to defer performance optimization. We've been taught that in programming school. It says, oh, we don't talk about this because it often adds complexity. It makes code unreadable. So it's often not something that we pay attention to. But if you stick with me, I'll show you how you can have your cake and eat it too. So in our universe, this is how most sites currently work. So this is the start of the movie. All right, so I have several waterfall diagrams for you to contemplate at this point, right? The first row, is my mouse visible? Can people see my mouse? Yeah, okay, good. So the first row is basically a full single page app style, right? The client asks for a page and then we deliver the HTML and the JS load, and this bluish color here. And then the client will fetch some data, sometimes sequentially, fetch this a little bit and say, oh, I decide I need a bit more, and I decide I need a bit more. And then at the end of it, we do a little bit of client rendering, and then we get an output right at the end. Nothing is visible until fairly late into the picture. Now, the second row is, let's push some of this responsibility to the server, right? Especially the network, the data fetches. If I know that if I'm fetching this, then I need to fetch the next, and then I need to fetch the next. Something like GraphQL is great for these sorts of things. So we have that sort of server assistance, and it helps eliminate some of that network back and forth that's happening. So that's our second row here. We managed to bring forward the time in which our content is visible by a little bit. Now, third row is considered state-of-the-art today, which is basically, we do some sort of a partial server-side rendering where, your really, really important data, you fetch it on the server side, and then you render that HTML on the server side. Right? It improves the perceived performance of your website, but that brings that green back to the front, but it actually adds a little bit more to the total time compared to the second line. Now, in all of these solutions, we actually end up using a ton of JavaScript in the client, right? 500K onwards is not uncommon. For example, React, 30 kilobytes. If you're using a meta framework like Next.js or Remix, that's another 40 kilobytes. You use Apollo on the front end, that's another 40 kilobytes. You throw in some internationalization, that's another 30 kilobytes. And that's before you even started writing any of your own code. So in the end, 500K is normal for these days in this universe. So the net effect is, this is a Datadog Core Web Vitals analysis of this website that I was working on. The Core Web Vitals are great because it measures everything the user experiences. So from anything from the network conditions, so the size of your bundle is already included into this measurement. The order in which you download your assets also kind of included in this, as well as the device capabilities. How fast does it take for the device to actually crunch through all these things? Cool. So some of this distribution that you're seeing on the screen there is actually from the server response time itself, because the server sometimes takes variable amounts of time to complete things. But the bulk of this time that's being represented here is due to network conditions of your real users and device conditions of your real users. Now, keep that in mind while I take you on a journey to a different universe. So let's go back to this diagram. I've added 2 more rows this time. Now, the big switch here is that we're moving away from a client-centric universe where the client does everything to a server-centric universe where the server does everything instead. So in the 4th row, you can see that I've got a full server-side rendering on the server. So the server fetches all of the data, server renders all the page and sends it off to the user. That's not so good because it means that you don't have any content until you have all your content. So it's not great, but we can improve on that. And that's the last line there. The last line is server-side rendering with streaming. So I'll go through this in a little bit more detail. When the client requests for the page, this A chunk here, the server can basically immediately respond, give you 200 OK. Oh, by the way, fetch this JS, fetch this CSS while I'm still thinking. So the server fetches some data, does a database lookup of some sort. And then, hey, I've got enough data to render this next chunk. So I'll send that B and I'll shoot it off immediately for the browser to consume. I'll continue fetching the data and I'll send that off. I'll continue fetching data and I'll continue to send it off. So the fragments basically arrive as soon as your data is being resolved, right? There is no overhead anymore. Everything just happens really nice and fast. And if in the ideal scenario, if these things are basically top down, like whatever's at the top of your page renders, is fetched fastest, then you basically have a really, really fast response time that you basically have your data being available immediately to the users. Now, this diagram is not to scale. Obviously, there's no notion of scale here, but you can start seeing that we can actually approach that 10x, right? This green diamond up here that you see, this is the end of things. That's basically been brought all the way to the front here. We can actually have our 10x. Next thing to think about is, well, we talked about network variability and we talked about device variability. So the next question is, do you really need that JavaScript? Can we actually deliver websites that have very, very little JavaScript? So let's step back and think about it. So what does JavaScript do on the front end? Right? Let's just assume at this moment that progressive enhancement is a thing, right? That we can actually lean on the core browser capabilities to do the links, to do the back and forwards, to do the the form submissions using get and post, all the native form things. So if you lean on the browser, then really the bare minimum JavaScript you need is the one that reshapes the DOM. Right? You know, bring that modal in, make this thing slide in and slide out and that sort of stuff. That's really the only thing you're doing. You're trying to reshape the DOM. Everything else, you know, virtual DOM, fetching additional data, skeleton screens, error messages when those screens fail and stuff like that, it's overhead, right? So all we need to do is just figure out how can we deliver the minimum amount of JavaScript to reshape the DOM. So I'm going to introduce you to this picture here. So the leftmost one is probably where we're at the moment, right? This is our, let's just say our React tree and our tree of components. If really only the circled components are the components that actually changed, we still delivered all of that JavaScript for the entire tree. And when we come to re-render anything, we basically have to re-render the entire tree, even though really only those two things actually changed. We could optimize this a little bit and go to the one in the middle, which is subtree hydration. But recognizing that, look, if this is the component that's at the top of a tree that actually is dynamic, if I only bundle the components for this little subtree and this little leaf node at the end, then I can actually have a bundle that's a lot smaller and also have a runtime that's a lot smaller. But then you say, can we make it go better? Yes, you can. Is imagine if you could somehow be able to selectively only hydrate this. If you can actually figure out that, look, that is the node that's the only node that changes. So I'm going to send just enough JavaScript to reshape the DOM for that particular one node. So the bundle size is really nice and small, and the runtime is also really nice and small. Everything is really, really nice and quick. So I made a 10x claim. Is that true? So in this site that I've worked with, I ended up with, this is an e-commerce website. I ended up with HTML that's about 15 kilobytes, JavaScript is about 20 kilobytes, and CSS is about 3 kilobytes, all these compressed sizes. And in this particular case, it represented 10x, 35x, and 20x, significantly smaller than what the thing is. I'll show you again in the next slide how these are actually vanity metrics. But one thing I want to point your attention to is these graphs on the right-hand side here. So the top one is the before graph. You can see that we have a response times that's measured in the multi-second range. And over here on the bottom one, which is the new one, which with HTML streaming and stuff like that, we actually have, and apologize for Chrome choosing green and blue because they're both so similar. The green bar here is basically us waiting for that first response from the server. As soon as we get that first response, we also get told at the top of the HTML, hey, go fetch this CSS, go fetch this JavaScript. So these JavaScript files and this style sheet here is being fetched while the server is still thinking. Say, let me go fetch that data, let me go fetch that data. And so this blue line here is the server executing its thing, but the CSS and the JS, which is already quite tiny down here, you can see that they're only measured in a few tens of kilobytes, can be downloaded ahead of time. In this particular case, the server was in America and the measurement was taken in Australia. So really, this 250 or so milliseconds is due to that, around the world latency that we have to deal with. So imagine if a user was in America, where or the server is in Australia, that 250 milliseconds basically just disappears. You get a response time that's basically, just like that. Okay. Also, these two. One thing to note here is because of Chrome's auto scaling, these two things are not completely to scale. So it looks like this one is worse performing, but it's actually the one better because of the different time scales. Okay, so back to this. Right, I said those metrics, yeah, sure, you got a smaller CSS, sure, you got a smaller JS and all that. It doesn't really matter because ultimately what we care about is the actual real user performance itself. So this is the graph of the updated streaming HTML solution that we've got. And you can see that the P75 is under 1 second compared to what was there before, where the P75 was multi-seconds long. And so, we get a significant improvement in the largest content pane, the first input delay, which basically measures how busy your device is in crunching through JavaScript, is now in the less than 10 millisecond range compared to the tens of seconds, tens of milliseconds that was there before. Okay, I believe everything else on the left I've already spoken about. Okay, now this is not just limited to the client as well. It's also a benefit to the server as well. Because in theory, the bare minimum the server needs to do is basically just string concats and some awaits for your data to arrive, right? That's the bare minimum the server needs to do. So, if we switch to this new thing that I'll introduce a bit later, you can basically have less CPU work per request, and you significantly reduce the event loop delay. On the top right picture, that's with the old system that I started with React rendering. The React rendering was taking 300 milliseconds or so, doing its thing to generate the server-side rendering. And in that time, any request queued behind it will have to pay that price of the event loop delay. And imagine if you were 3 or 4 requests behind, you're paying for the wait time of the request in front of you. So you kind of need to over-provision your servers to offset some of these things. The streaming HTML solution, which is basically just string concats plus some awaits, the event loop delays are measured in the single-digit milliseconds, so it's quite significant. And also with streaming, one thing to bear in mind is that you have less memory consumption because you don't have to keep everything in memory, right? You get a little bit, and you just flush it out. You get a little bit, you flush it out. And this kind of points towards your backend solutions also wanting to have streaming things. So you're encouraged to use things like new line delimited JSON so that you flush things out as quickly as possible. You use protobuf. Protobuf with HTTP2 is gRPC. Everything is streaming by default. That should be preferred over things like GraphQL, which basically encourages you to bundle everything together, collect everything in one big chunk, and then shoot it off. But performance equals complexity, right? We've all been taught that at programming skill. Well, that's true if you stay in the same universe, but if you allow yourselves to change, you actually get a massive reduction in code complexity as well. So this is a fairly common pattern that lots of places use. When your browser gets data from your initial HTML server, but then later on fetches data from JSON or GraphQL or something via some separate BFF server. But if you shift all of the complexity to the server, that red box there disappears. We just don't need the red box anymore, right? So we don't need that parallel code path. We have reduction in our security footprint, runtime concerns, and all that sort of stuff. In the demo that I built, the lines of code was different by a factor of 15 times. So it is quite significant. And part of it is because I eliminated half the code that didn't need to exist anymore, but also because I removed a few years of craft and dead code and stuff like that. So it's not quite a fair comparison, but still, we're still talking about close to the 10x range anyway. Okay, rabbit holes. What's the problem with doing this? All right, one of them is that your server load actually becomes more bursty, right? Because you're doing everything, boom, all at once now. It's a much burstier thing. So you got to be careful that your backend is able to cope with the increased burstiness of traffic. But you can kind of offset that with fragment caching as well, because everything is kind of funneled through the server now. So you can actually put a Redis cache of some sort in that server to basically reduce the number of duplicate requests that you need to make. Something like an e-commerce site would have a banner at the top, buy now or sale on or something like that. That banner, you don't need to do a database lookup for that banner all the time because you can actually cache that. Even though the page itself is not cacheable, the banner is cacheable. So you use fragment caching, and that helps offset some of that server load. And the other thing that is in a rabbit hole as well is what happens when there is a server error after you've initially said, hey, this is good. Right, you send a 200 OK, and then in the process of fetching additional data, something's gone wrong, right? So you can deal with that in 2 ways. For humans, well, that's easy enough. We just render a box that says, something's gone wrong. But for machines, what we can do is we can hang up that HTTP response, right? This requires HTTP2 end-to-end to be able to do that correctly. But if you have a dig through the HTTP2 specifications, you can see that there are mechanisms built in there that basically allows you to say, yeah, it's broken now. So for bots, don't cache it and don't index it because it's broken. So you can do a few things there. All right. Now, I hope I sold you on what can be done. Now, so hopefully your question might be, okay, how do I do this, right? And drum roll, I built this using Marco, which is an eBay technology. They've been around for as long as React has been. So it's not some new kid on the block that's just introduced recently. Its main features is basically everything that I've talked to you about, right? It can do HTML streaming, fetching data while it's rendering stuff, and it can do partial hydration, which is that diagram I showed you of the tree where only bits of the tree needs to be hydrated on the client side. But they're not the only ones out there. I'm sure you would have heard of React Server Components, React Streaming. They're all trying to do the same thing. So yeah, it's a space that's actually very actively worked on right now. Marco, I believe, is the leader at the moment, but of course, anyone else can come in and leapfrog them in the future. Also bear in mind though, if you're hoping for React to solve the problem, just take note that React is 40 kilobytes to start with, and Marco can complete the thing in 20 kilobytes. So take that into consideration as well. Finishing off soon, just a quick preview of what the code kind of looks like. So this is Express.js code. I apologize, I didn't get the syntax highlighting to work. It's just all black. But basically, what the server needs to do is fetch some data. If you can't fetch some data, then it's 404, right? Just because it meets the regex for that path doesn't mean that the asset exists. Or if there's an error at that point in time, you can do your regular 500. At that point, you can hand over to the Marco runtime on the server side to start rendering. And this is what it looks like. So pretend you have some widget that has a sub widget, a couple of sub widgets over on the inside. You can see that the sub widgets can wait for some promise and then renders some stuff. All of that happens while rendering. So you're rendering and fetching data at the same time. All the promises are resolved eagerly in parallel. And it's co-located into the component itself. So what happens here is that whenever the promise resolves, you have the opportunity to flush that HTML to the client. Sometimes, like I said, ideally what you want is the top of your HTML to be flushed first, then eventually work your way down. But sometimes you kind of need to invert the order. Like it just happens that the top part is critical, but is slow to evaluate. So you can add a placeholder element and it will reorder that with JavaScript once the bit is done. Last slide. This is a real world waterfall diagram of what this thing actually looks like now. So in this particular case, the bits on the left side is the data lookups that needs to happen before you render. In this particular case, they happen to be sequential, but that's irrelevant. Right, so at this particular point in time, you can immediately deliver your first byte. So that little diamond here indicates, yep, I can deliver my first byte. And then I'm going to fire off all my promises in parallel. So there's 4 in this particular case, 4 different promises that need to resolve to do the data lookup. As soon as any one of them is done, those dots up here on the top right are basically points in time where the HTML is ready to be flushed to the client. It says, I've got some data there. I can flush this. I can flush this. I can flush this. So you basically get something that's really quite fast. So I hope by now that I've managed to convince you that there is a different way of doing things. Server-side rendering was how we used to do things until we got sidetracked about 10 years ago when Angular first hit the scenes. But yeah, since then, we've been doing client-side stuff that to a lot of new developers is the only way we build stuff. But if you consider moving back to a server-generated paradigm, consider using a streaming technology, and you'd be surprised by how fast the performance is and how fast you can develop as well, because you don't have to build half the things. That's it.